Welcome everybody. Today we're going to start talking about a lesson of spectroscopy and in more details about mass spectroscopy. So before we go to the mass spectroscopy in here, let's talk about what is meaning of spectroscopy as a science. So the spectroscopy as a science indicates, or it's a science that studies the interactions between light and matter. And the matter here represents the chemical compounds or generally the organic compounds that you have. This powerful technique, the mass spectroscopy, can tell me a lot of details, such as the atomic mass of a certain element in the presence of the isotopes. It tells me about the molecular mass of a certain compound. It tells me about the presence of a chlorine or bromine atoms in my molecule, in addition to the number of carbon atoms in my molecule. In the early classes, and this year, we started with the spectrometer, which is a device that tells me about the atomic mass of a certain element. If you go to the periodic table, for example, you can go to the atom of neon and you can notice that the Ne has an atomic mass of a 20.2. You have to put in your mind this atom or this element contains, or let's say, appears in different number of isotopes in nature. And these isotopes, as we can see, we have neon 22 in here, we have neon 21 and neon 20. So from these information, as we can see, we can deduce the atomic mass of neon atom. Okay, so how can we do this process? First of all, you have to put in your mind the mass spectrometer gives you a spectrum that looks like a y-axis and x-axis. The x-axis represents the mass per charge ratio, or M per E, and the y-axis represents the relative abundance. So according to this graph in here, we can deduce that a neon element contains three isotopes, as we have three columns in here. Their percentages are written in here, you can see. The most abundant isotope is neon 20, and the least abundant one is neon 21. The first thing that you have to do in here, you have to multiply the percentage with the mass in here, and then you say plus the mass times the percentage times the mass, and then plus the mass, the percentage times mass. How can I do this process in here? I just want to write it again in a better way. We can say that the AR is equal to 90.9% times 20 plus 0.3% times 21 plus 8.8 times 22 over, what is the summation of these percentages in here? You can say it's 90.9 plus 0.3 plus 8.8. These are the percentages, and then you can calculate the ARN equals to 20.2. And this number actually is represented in the periodic table and the neon of Ne. And you can say that, oh yeah, this is the average mass of the isotopes of neon in here. So this is the answer at that point. So let's go to the another one. How can I deduce the mass spectrometer of the things? But in your mind, I just want to give you a simple example. CH3, CH2, CH3. At that point, I need to calculate or to determine the MR. One of the good things that the mass spectroscopy, an instrument or technique, can tell me is the MR of your organic compound. Okay, so once you insert a chemical or let's say the organic compound in this instrument, it will give you the MR. But what is the procedure? Actually, it's not included or it's not covered in your A levels, but it's a fun fact to know about it. As a result of applying a source of light, because we're talking about spectroscopy, the interactions between light and matter, we're applying a light to this molecule. As a result of this strength of this light, one electron is removed. Okay, and that's why this molecule in here becomes positive, CH3, CH2, and then CH3 with a positive sign. This compound that has or carries a positive sign, it will hit the detector. And the detector actually, it's a part of the instrument that it works as an indicator. So once this touch the detector, it will give you immediately the MR of this compound, and it will be appearing in like this form. We have the same spectrum that we saw in the isotope. You have M per E. Actually, it represents the mass or the molar masses, and the y-axis represents the relative abundance. It's the same thing that we covered in the isotopic masses. So at that point, you will notice that as a result of hitting the detector, okay, you will notice the presence of peak in here, and it will appear at 44. And by the way, 44 actually represents the MR of this compound. And we just want to talk about this part later, but don't forget we have a little small little baby peak and appears at 45. This guy in here appears at 45. What do we call the peak that appears on your right side? Okay, here, the only one that appears on the right side. Okay, it's called M plus, and it has another name, which is molecular ion. Okay, the molecular ion actually is represented by M positive, and it's the same as the MR. So if I ask you about the MR of this compound, you can say, okay, we start reading it from the right. Okay, ignore this small guy in here. I don't talk about it here. I don't care about it here so far. And then we take the other one. We have another thing to be discussed as well. If we have, let's say, a peak that appears at 15 and another one that appears at 29. Okay, what do these things in here represent? Okay, I told you that this molecule carries a positive charge. Okay, but this positive charge makes the compound unstable, and that's why it will start fracture into fragmentations. It will start to be broken from here or in here. So as a result of breaking from this side, from the first part of the methyl, and let's calculate the MR of methyl. You have carbon 12 plus 3 hydrogens equals 15. And you notice that this peak in here represents the fragment of CH3 positive. So if I ask you, what does the number 15 actually in here represent? Which fragment? It represents the fragment of CH3. Okay, what about the 29 guy in here? Okay, we told you that this is a chemical compound. It doesn't understand. The fragmentation doesn't take place in a systematic way. Actually, it takes place randomly as a result of removing this electron. Nothing happens. Or let's say you do not expect anything. So here we have CH3, CH2, CH3. As we told you, this guy is unstable. So if we have a breaking that takes place in here, and we got this fragment carries a positive charge and then start to hit the detector again. So if you calculate the MR of these two guys in here, the two carbons and their hydrogens, we can say, oh yeah, this fragment in here, the 29 guy, he represents the C2 H5. And don't forget the positive sign. You have to indicate that this is a positive sign. What is the importance of these fragments? Do they tell me something, or should I just guess these fragments? The answer is both. The fragments can tell you a lot of things about the structure of your compound. The question is telling you that you have a ketone, Z. It consists of 5 carbons, 10 hydrogen, and oxygen. So the first thing that can hit your mind, actually, you can say the MR of this ketone is what? You have to start reading it from the right, and then ignore the small guy in here, we don't talk about it, and then just like this one. Okay, this target here is my compound. So what is the MR at that point? Actually, you can calculate the MR from here, but to make sure more, let's say an extra thing to be discussed in here, you can say it's 86. Okay, so the MR is 86. I can guess it from here. The ketone here consists of 5 carbons. Okay, let's make 5 carbons. 4, 5, and then we have another one. Okay, 1, 2, 3, 4, 5. Okay, it could be in the second carbon or in the third carbon. Okay, so which ketone that we have? And we can have another ketone that takes the same molecular formula and looks like C, and then here we have C double bond, C, and then you have 2 carbons. Okay, these ketones are possible ones that you could have. And now let's check which of these things that work. Okay, the question is asking me in here, use the information to suggest the formula of the fragments with M per E peak at 29. 29, we discussed this guy before, and if you remember, it consists of an ethyl group you can see here or here. My question, I can take this fragment from this compound. We have a C2H5, and we can make a fragment from here. But if you look at this compound, can I take a fragment of methyl? I cannot break it from here. And I cannot if I break it from here, okay, but if I need, you can see that you cannot, it's not possible to break these compounds at the same time in order to have C2H5. So we can exclude this structure from the structures that we have. And if they ask me about what is the identity, if they ask me about this fragment, it's going to be C2H5. And don't forget the positive charge. Let's go to 57. Okay. Since we have two possible structures so far, you just want to use my calculator and then you start guessing the questions. We exclude this guy in here. We don't need it so far. Okay. You're excluded. I cannot take an ethyl group. You can deduce from this guy in here. If you don't have a fragment of C2H5, then the structure is not the one that we needed, actually. I will use my calculator. Okay, let's take the first guy. By the way, like 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. Okay, I just want to use my calculator, actually. There's no specific rule for this. So if we take a fragment from here, it's 15. Okay. If we say like 15, and here we have 16 from this oxygen and from 12, what will be the answer at that point? It's 43 so far, and now let's take another carbon. Okay, plus 12 plus 2 hydrogens. Oh yeah, I can deduce that this fragment here, okay, represents a fragment of 57. So I can represent this. How many carbons we have? 1, 2, 3, then it's C3. How many hydrogens we have? 1, 2, 3, 4, 5, H5. And how many oxygens? We have only 1. Okay, and don't forget the positive sign. Okay. Okay, it's a possible answer. Can I do the same thing in here in this structure? Okay, this is, yes, I can take this, by the way. This fragment is the same. It's C3, H5O, and positive. So both fragments can work. So yeah, it's C3H5O positive. And the question here, the last one, is telling me to identify Z. So it could be two possible answers. You could have this guy in here, 1, 2, 3, 4, 5. The double bond in the middle, or it will be on the second carbon. So both work. Why do they both work in here? Because we can have a fragment of C2H5, okay? We could have a fragment that contains 57, that includes those guys in here, like this. Okay, so both work, and that's why it works for that. The question says, Z is a molecule which contains element carbon, hydrogen, and oxygen. Okay, CHO. Z contains only alkene. Okay, it means C double bond C. Carboxyl, which means carboxyl group C double bond OH. Okay, these are the only functional groups that we have in here. A says, complete table 6.1 by describing the observations that occur in the two different reagents added to separate samples of Z. So if we add Br2, you have to put in your mind that Br2 has a target, which is the alkene group, and actually it decolorizes or changes from orange to colorless. And for metal carbonate, you notice that the metal carbonates react with acids, and as we have a functional group of carboxylic acids, we can say, yeah, you have a lot of fizzings or bubbles. So these are the possible answers. Okay. The question says 6.2 shows the percentage by mass of each element and Z. Using the data and table in here, demonstrate that the empirical formula of Z is CHO. Okay, we can say CHO. And then we have to divide 4.138. Okay, this is the mass percentage. The hydrogen is 3.45, and for oxygen is 55.17. We determine the empirical formula by dividing over their atomic masses. It's over 16, it's over 1, it's over 12. And then the answer is going to be 3.41, it's going to be 3.45, and it's going to be 3.42. Their ratios is 1 to 1 1, and that's why the empirical formula is CHO, which means they have the same ratio. All right, the question is the mass spectrum for Z. Z, remember, it contains, it has empirical formula of CHO. It contains a carboxylic acid and alkene. You have to put it in your mind so far. Okay. Now we have a beautiful graph in here. Okay. And if I ask you what is the MR of this compound, you can ignore the small guy in here and just take the longer guy, and actually it's 116 gram per mole, which is the molar mass. Okay. The question here says, deduce the molecular formula of Z, molecular, I mean the MR, and explain your answer by referring to the molecular ion peak. Molecular ion peak, put in your mind, it represents the value of M plus 1. This is the M plus, the longer peak, which is 116. And the question is telling me how to determine the molecular formula. I mean, like it's C5H5O5, for example. What is the value in here? The ABC of the O level, we can take the MR of the molecule over the MR of the empirical. And if you can see here, we have 116 over, what is the MR of the empirical? It's 12 plus 1 plus 60 to 29. If you divide this over 29, it gives you 4, which means that I have to take this 4 and just multiply it by CHO. And then the question, or the molecular formula, is going to be C4H4O4. In other words, in our compound, we have 4 oxygens, 4 hydrogens, and 4 carbons. And we have alkene and carboxylic acid. These are the only functional groups that we have in our compound. The question is asking me about these fragments, like 45 and 71. Okay. So I have to say, okay, since we have carboxylic acid, I have to write the functional group of carboxylic acid. Let's say it's C double bond OOH. We have alkene group, we have CC. Okay, so far we have 3 out of 4 carbons used. Okay, what does it represent? If we use your calculator, by the way, and then calculate the fragment in here, the carboxylic group, 16 plus 12 plus 1, then it equals to 45. Then I can say, yeah, it's CO2H positive. Okay. The next guide is telling me about what does the 71 fragment represent. So we have 45 so far. We have to add more carbons. Okay, just want to take them in different color. Okay, these guys in here. Okay, don't forget their hydrogens. We have hydrogen here and hydrogen here. Then we can say, okay, 45 plus 12 plus 12 plus 1 plus 1, and equals to what? Okay, let's use your calculator, and equals to 71. And we can say at that moment that the whole fragment here represents the other guy, and it's C3. How many hydrogens we have? 1, 2, 3. H3. How many oxygens we have? O2, and don't forget the positive sign. Okay, but you have to put in your mind, okay, we're done with these fragments, but we didn't finish the whole molecule. If you look at here, okay, we still have missing part. So what do you think these missing parts are? From the question that tells you that you have only a carboxylic group in here, and we have alkenes, double bond. What could be the other part, the missing part of this here? We cannot put alcohol because the question doesn't tell me about the presence of alcohol. It's not aldehyde, it's not ketone. And which of these functional groups can give you a compound that contains oxygen? We can say it could be diacidic or diacid part, and that's why we have to put the other part of the acids. You can see that you have you have 4 carbons, you have 4 hydrogens, you have 4 oxygens. And now let's talk another thing that this powerful technique can tell, which is the number of carbon atoms. Yeah, it tells you about the number of carbon atoms. But how can I determine the number of atoms of carbon? You have to memorize this relationship in here. It's 100 multiplied by m plus 1, the abundance, put in your mind, and it's 1/1, abundance and positive. How can I apply this rule? The combination of mass spectroscopy and MR provides a powerful method of analysis of organic compounds. The mass spectrum of a compound J, M and M plus 1 peak ratios. Put in your mind once they say like ratios, M and M plus 1 ratios and their heights, they're talking about the relative abundance, okay? The heights, the abundance. So these are the abundances. It's always M is greater than M plus 1. Okay, it's the taller guy, if you remember that, and the small guy is represented by M plus 1. I just want to draw a bit something that makes some sense for you. This is M plus, and this is guy here, it's M plus 1. So the height of M plus is equal to 74, and the height of M plus 1 is equal to 2.5. And that's why it's very small one here. Why do we have these guys? We just remember something from the carbon atoms. We have carbon 12, we have carbon 13, and carbon 14. And forget about carbon 14 so far. I don't care about it so far. We have carbon 13 and 14. The most abundant carbon is carbon 12. And I don't remember the percentage, but it was very, very greater than the percentage of carbon 13. And sometimes in your compounds, I mean the organic compounds, you could have, or definitely you have a carbon 13 and carbon 12. But the carbon 12 is greater than carbon 13. And that's why we have M for 12 and M plus 1 for 13. So the plus 1 here indicates that you have an isotope of carbon, which is carbon 13. Okay, so how can I determine the number of carbon atoms based on their heights? Okay, so the rule says we have N equals to 100, okay, multiplied the abundance of M plus 1. What is the abundance of M plus 1? This is the abundance of M plus 1, which is 2.5. And then you divide it over 1.1. It's a part of the law, and multiply by the abundance of M positive, which is 74. And then you just apply some calculations, and the answer is going to be 3 point something. Okay. But since we're talking about the number of carbon atoms, we have to take an energy number, and that's why it's 3. So you have 3 carbons in your compound. It says the relative abundance of molecular ion peak and the mass is 62. Relative abundance of molecular ion peak, which means the height of M positive. Okay, and this is 62. And the compound that you have here is ethylamine. By the way, this question is from the A2. It's not from the AS. And the amines are included in there, so it's not included in the AS. But I just want to let you know that the ethylamine looks like CH3, CH2, and H2. And from here, you can determine that you have 2 carbons. Just like put this in your mind. And now the question is asking me, calculate the relative abundance of M plus 1 peak in this mass spectrum. Okay, I can say, okay, I have a number of carbons, and this is the missing part. I don't know it. We have 100, it's already in the law. 1.1 is already in the law. And the height here is equal to 62. So we can say we have 2 carbons. It's 100 multiplied by M plus 1. And we deal as M plus 1 as 1 unit. Okay, and then here we have 1.1 and multiplied by 62. We can say M plus 1 is equal to 2 times 1.1 times 62 over 100. And then the answer is equal to, here is the answer. It's equal to 1.36 or 1.4. So the relative abundance of M plus 1 is equal to 1.4. And it's very small with respect to this value in here. It's very, very small.